Hey everyone, welcome back. Over the last few lectures we've discussed a couple of topics. The first one, spanning set, or this idea of spanning, and the second one was linear independence. And I said they're both in the top 5 when it comes to important concepts in linear algebra. And part of the reason is because of this definition that I'm about to write down, which actually combines both of those concepts into one definition. So here we go. A subset capital S is, or of a vector space V is a basis for V if two things happen. So we're defining this concept of basis. A subset S is a basis if, number one, S is linearly independent. And second condition, the span of S is equal to V. So a basis is a linearly independent spanning set for our vector space. Okay? So let's write down some quick examples here. Some of these we've already looked at before. So for example, E1 up through En. Remember, these are the column vectors that have, so Ei is the column vector that has a 1 in the ith position and zeros everywhere else. Right? This is a basis for Rn, and it's actually called the standard basis for Rn. So in the future, when I say the standard basis for Rn, that's the one that I'm talking about right there. Right? We've already seen previously that the span of this set is equal to Rn, and in the very last lecture, I guess that was lecture 18, we saw, or I wrote down and said you should verify that it's linearly independent. Next example, if we look at the polynomials 1x, x squared, dot, 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 up through x to the n, this is a basis for p sub n, and this, once again, is the standard basis for Pn. So when in the future I say standard basis for Pn, this is the one I'm talking about. And so what this means then, or what you should notice from the words I'm saying here, vector spaces can have more than one basis, right? So this is one particular example of a basis for Rn. This is one particular example of a basis for P sub n. And we'll see other examples. Let me write down one more standard basis. This is the one for our vector space consisting of matrices. Capital E sub ij, where both I and j, so I less than or equal to m, and j less than or equal to n, right? So the set collection of all possible E sub ij's, this is a basis for m sub mn, and this is the standard basis. It's not the only one, but it is an example called the standard basis. Okay, so now for our next example, let's consider this one right here. So my claim is that the following set, so it's going to be some column vectors 1, 1, 0, and then 1, 0, 1, and 0, 1, 1. So the claim is that this is a basis for R3. To verify this, I need to show that we're looking right here at a linearly independent spanning set. So let's say reason. And what I'm going to do first is show that the span of those 3 vectors is actually equal to R3. So that means that I want to choose an arbitrary vector. I'm going to call it x, y, z in R3. And then I'm going to set up, we're going to solve the system A times the first vector plus b times the second vector plus c times the third vector equals x, y, z, right? I want to show that every arbitrary vector in R3 can be expressed as a linear combination of those three. So if I can find an A, B, and a C that solve this, then we get it. Now, so the next step here, this system right here corresponds to an augmented matrix, 1, 1, 0, 1, 0, 1, 0, 1, 1, x, y, z. And you go through the row operations. I'm going to get it in reduced row echelon form. And you don't have to go through all the steps. I'm making this a little bit taller because I know what the answer is going to look like. When you do it, on the left-hand side, it's not hard to see that you're going to get the identity matrix, and then the far right column looks like this: x plus y minus z all over 2. And then the next one is an x minus y plus z all over 2. And the last one, y minus x plus z all over 2. All right, so what is that saying then? It's saying, and so let's actually write what this means. What we have here, when we choose an arbitrary vector x, y, z, this tells us exactly what A, B, and C need to be. So what we have is x plus y minus z over 2 times our first vector, 1, 1, 0, plus b is going to be x minus y plus z all over 2 times the second vector, 1, 0, 1, plus y minus x plus z all over 2 times the third vector equals x, y, z. So if you tell me x, y, and z, I'll tell you exactly what A, B, and C are. I'll throw them into the formula. That tells us then that every vector, x, y, z, can be expressed as a linear combination. So span of that set, can we just, to be efficient here, let's call this set capital S. Then I can say, so span of S is equal to R3. Okay, so we're halfway there. Next, I need to show linear independence. So, let's like this. So now, suppose that A times the first vector plus b times the second vector plus c times the third vector, 0, 1, 1, equals the 0 vector. Right? To conclude linear independence, I need to show that the only solution to this equation is the trivial solution, A equals B equals C equals 0. Now, from our previous formula, notice this formula tells us exactly who the solutions are going to be. From that previous formula, it tells us then what? Well, let's see. So if I have a 0, 0, 0, it tells us, right, plug 0, 0, 0 here, we get 0, 0, 0. So from our previous formula, all right, the exact solution is given by this right here from our previous formula. A equals B equals C, which equals 0. Therefore, that set S is linearly independent. So now that tells us that S is a basis. Right, so conclusion, S is a basis for R3. I want to just think about, before I move on to the next example, I want to think about what just happened here. What we did, and I want to write it in matrix form, we solved the equation AX equals B, where our coefficient matrix consisted of the columns right there, and then B was my vector X, Y, Z. And what we did is we showed that this system had a unique solution for each choice of B. And also notice our coefficient matrix right here was a square matrix, right? So, and showed unique solution for each B. Now, from the equivalence theorem, so this is true, right? So by the equivalence theorem, unique solution for each choice of B, that's true if and only if A is invertible, right? If and only if the determinant of A is not equal to 0. So in the special case where we have a square matrix for our coefficient matrix, which would then mean that, right, when we're working in R3, that we would have needed 3 column vectors, we can actually show that we have a that we have a basis by just computing a determinant. So let's kind of summarize that. So let me put stars around here. So to check that V1 up through VK, let's use an N. Vn is a basis for R sub n, right? So now we need a match here, right? So that the coefficient matrix is square. Set up the appropriate system, AX equals B, and then we get a basis. How's this go? Let's see it over here. If the determinant of A is equal to 0, then it's not a basis. If the determinant of A is non-zero, then we have a basis. And notice, I mean, really, you don't need to set up this system. All you need to do is identify the matrix A. Who's the matrix A? It's the matrix consisting of the column vectors in the set that you started off with. Compute the determinant of that matrix, and that answers the question. Now, I've stated this in terms of Rn, but we can actually generalize this a little bit anytime that we have a square matrix. So let's see, let's do the next example. I want to show that the following set here, so this is 1 plus x, x squared, and x plus x squared is a basis for P sub 2. Okay, now how would we go about this directly? So the solution, and let's call this set S. So I'm going to call it capital S. So the solution, S, is linearly independent if and only if So let's write it like this: a times 1 plus x plus b times x squared plus c times x plus x squared equals the zero polynomial only has the trivial solution. Now, let me rewrite this, I guess. So let's write it out. This is a plus c times x plus b plus c x squared equals 0. So if I just join the coefficients, did I screw something up? A plus c. No, that's right. Okay, so now, so that would be if and only if this one has only the trivial solution. And now, so let's write that out. If and only if a equals 0, a plus c equals 0, and b plus c equals 0. So I'm writing this now, and so let me think now, how does this go? This course, so if and when this has the trivial solution. And now, if I set up the corresponding augmented matrix, so if and only if 1, 1, 0, 0, 0, 1, 0, 1, 1, and then I have 0, 0, 0, has only the trivial solution. We know that this system right here is consistent, right? It's a homogeneous system. So what are our options? Exactly one solution or an infinite number of solutions. We will have an infinite number of solutions if and only if we have a free variable. And so when is this going to occur? So this is if and only if the determinant of the corresponding matrix 0, 1, 0, 0, 1, 0, 1, 0, 1, 1 is non-zero. So if I compute the determinant here, that's going to be a 1 times negative 1. And so from this determinant computation, because I got non-zero, I can conclude that we had a basis. I know I went through a lot of steps in this case, right, to sort of develop why this works. The point is, even when you are talking about bases that are not in Rn, when you're not working with column vectors, you can use a determinant as long as the corresponding coefficient matrix is square. Okay. So since this determinant is non-zero, we're done. I hope that makes sense. Yep, I don't know what else to say. Okay, so I've seen a couple of examples where we have a basis. So now I want to do is show that the following set 2, 0, 1, 0. So now we're looking at matrices in M22. 0, 1, 0, 1, and 1, 0, 0, 1 is not a basis for M22. Get thirsty, I need a drink here. Okay, so for our solution, let's consider, so it would look like this: A times 2, 0, 1, 0 plus B times 0, 1, 0, 1 plus C times 1, 0, 0, 1. And now, if I want to show this not a basis, what I'm going to do is show that this set here does not span all of M22. And so I need to find some particular matrix that's not in the span. And so I think I'm going to do, how about this one? 0, 1, 0, 0. Okay, now the corresponding system will look like this. 2A plus C equals 0. B, I should have spread this out a little better. 2A plus C equals 0. The next one, B equals 0. And then I'm going to have A equals 0. Oh, sorry, let me just think here. Sorry, B equals 1. Whoops, sorry about that. B equals 1. A equals 0. And then for the bottom corner here, it's going to be B plus C equals 0. All right, so A equals 0, B equals 1. So that tells me here, so I want to focus on this. If A equals 0, that means C equals 0. Right, from this first equation. So that one tells us that C equals 0. If C equals 0 and B equals 1, right, that would then tell us, so this one right here, if B equals 1 and C equals 0, well, we get a contradiction here. Right, because this would tell us that C has to, if B equals 1, then C equals -1 from this equation right here. So there's no solution to that equation right there, and so that tells us that the system is inconsistent, which means that we do not have a spanning set. So span of that set right there, let's call it S, span of S is not equal to M22, right? And so it's definitely not a basis because it's not a spanning set. Okay, let's see now for our next definition. If V has a basis of the form S equals, say, V1 up through V sub n, right, then V is finite dimensional. So what this is saying then, if V has a basis that consists of a finite number of vectors, right, then the vector space is called finite dimensional. If not, so if no such basis exists, then basis exists, then V is infinite dimensional. Okay, so it's not totally clear why at this moment basis is important, right? We're going to start seeing why. And here's one thing that will become more and more apparent. The idea of basis is going to give us a notion of dimension for our vector space. And so I'm just going to write down some examples here. We've already seen this, so Rn, Pn, M sub Mn. We've exhibited standard bases for each one of these, and guess what? That list ends. It's a finite list. And so these are finite dimensional. there are some that are not, and the most important one, so p sub infinity, remember that's the collection of all possible polynomials of all possible degrees. That one's infinite dimensional. Also f minus infinity, the set of all functions from R to R. So both of these are infinite. Dimensional. I'm stating this without actually providing a proof. It just turns out that it's true that both of these are infinite dimensional vector spaces. Now, why are bases important? Well, here's one reason. So if S equal to, say, V1 up through V sub n is a basis for the vector space V, and let's say little u is in V, so it's some vector, then there exists unique, I'm going to underline both of these, there exists unique scalars a1 up through an such that u is equal to a1 v1 plus dot 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 an vn. A basis, here's a way to say it, a basis is the most efficient spanning set, or the most efficient size for a spanning set. There's no redundancies. In that case then, for every choice of vector in V, we know that it spans, right? So we know, because we've got a spanning set, that U can be expressed as a linear combination here. In the case that we have a basis, not only can it be expressed as a linear combination, it can be done so in exactly one way. There's the uniqueness part. So the existence comes from the fact that it's a spanning set. The uniqueness comes from the linear independence. That's the efficiency part. Now, those numbers here, they actually have a name. So in the case that we have a basis, we can focus on these, or we're interested in those numbers right there. There's exactly one. So the numbers a1 up through a sub n are the coordinates of u relative to s. And there's notation for this. We write it like this. Square brackets around u sub s equal to the column vector a1 up through a sub n. So the coordinates, those are the unique numbers that you use to express u as a linear combination of the vi's. Right? When you have a basis, we have this notation right here. Or, so this is if we're thinking in terms of column vectors. Sometimes we want to write it as, I guess you call it in row style, in parentheses. So your book will sometimes use this one right here. If they write it using the comma delineated form, right, we'll put parentheses around it, sub s. But it's the same concept, either written as a column or as a row here. So for example, this set right here, 1, 1, and 1 minus 1, this is a basis for R2. We don't need to check this, and let's call this S once again. We're not going to check this. You can just trust me that this is a basis. And so now, let's see, if U is equal to the vector -1, 7, then you can check So then u is equal to, how does it go? 3 times 1, 1 plus, I think it's minus 4, yeah, negative 4 times 1 minus 1. So the coordinates of u relative to our basis s, like that, 3 minus 4. And there's a picture, if you like. So let's see, 1, 1. Is right there, and 1 minus 1 is right there. And then the vector negative 1, 7, let's say, is right there. So what this coordinate business says is, if you want to get to this vector, it looks kind of weird here, negative 1, 7, traveling in directions parallel to these two vectors, what you would need to do is travel 3 times this one minus 4, so go 4 times in, okay, 3, 1, 2, 3, I guess I was a little crazy there, and then 4 times in this, minus 4, my picture doesn't work very good, but minus 4 times that direction. The problem is I didn't scale this correctly. This should be longer. And I'm just totally blowing my example here, but minus 1, 7. So if you go 3 times in this direction and 4 times in this direction, negative 4 times in this direction, all right, you'll end up at that vector right there. That was a terrible example, but that's the idea. My picture's not very good. 3 times this direction plus or minus 4 times this direction will put you right there. Let's do another example. Okay, so now let's say S, and it's going to look like this. 1 plus x and 1 plus x squared. That's my set S. Oh, I already said that. So this is a basis for P3. Now what I want to do, I want to find the coordinates for a particular polynomial. So I want to look at the coordinates for, so let's say find the coordinates for the polynomial 3 plus 4x minus x squared sub s. The solution then is to express this polynomial as a linear combination of those 3 right there. And so I worked this out, so it turns out that 3 plus 4x minus x squared is equal to negative 1 times 1 plus 5 times 1 plus x plus negative 1 times 1 plus x squared. So what does that mean? 3 plus 4x minus x squared sub s is equal to negative 1, 5, negative 1. Okay, that's enough for today, so we'll see you next time.